Welcome. So today I'm going to be talking about essential Java for Android development. Android's a really fascinating topic that I've been fortunate enough to work on. I just wanted to share some of the best practices and tips and tricks that I've had working in the tech industry and also through some of my work at UCLA. So just to tell you a little bit about myself, so I'm a senior software engineer at UCLA. What that essentially means is I tend to be more of a generalist. You may find me working on a full stack mobile project, uh, could be a full stack web project. I've also done work in Unreal Engine 4 on VR, Python with machine learning. So my work tends to be, a little bit all over the place, which I really enjoy because it gives me a lot of variety in terms of the projects and the work that I get to take on. And in terms of my past background, I've worked for a variety of tech companies, primarily in the gaming space, but it's just kind of been a mix of a lot of different ventures and companies, some of my own. And really, what I'm going to try and do today is just give you a great ground floor, just getting started, getting your head wrapped around the best way of building an Android app, the ways that actually Google themselves and the Android team recommend, and really just putting you in the path to success for having a stable, robust app that is going to function, perform really well in the real world. So just starting off, let's talk a little bit about Java. So Java is a programming language. It's widely used in enterprise software. Uh, a lot of gaming companies as well as tech companies will use it in their backend services, writing a lot of their backend services in Java. And of course, it's used in mobile apps for writing Android apps. That said, while Java has all this power and flexibility to be working in all these different areas, by itself, it's just a language. It's not really any different from something else like C Sharp or a similar language that kind of is a little bit higher level. And there's a lot of frameworks out there that different companies will use depending on their needs that will extend its capabilities. So Java is the driver essentially of like where you're writing your code, and then which frameworks you actually end up using in conjunction really just depends on your project needs and what your goals are. So in the Android world, you can really think of the Android SDK as one of these frameworks. In the web world, it would be a different framework for doing server-side logic, uh, potentially like database management. But on Android, Java is essentially the driver into the Android OS. And a quick example of that would be you could use Java to write essentially a call into the OS to say, hey, I want to show an Android style pop up window, which I'm sure you've seen different apps that you've used. Or, hey, I want to go and draw a slider that looks like an Android slider. So, all of those different function calls are part of the Android OS, and the way that you're accessing that is through the SDK with Java. Now, backing up a little bit, just talking a little bit about the kind of the historical goals and context of Java itself. So, Java was designed to be simple, so intuitive. It was designed to be portable. The idea being that you didn't have to write a platform-specific code or really nitty-gritty specific code for writing for a particular processor or something going down to that low level, and then being efficient enough that it would essentially be usable in production apps and for real world software. In terms of the language itself, a lot of people, when they see Java, it's pretty easy to pick up. It's familiar, easy to learn syntax. It's basically modeled after kind of a C++ style of coding, which a lot of folks have had experience with, and it just tends to look pretty familiar and pretty friendly. One main feature of Java, and you also see kind of a similar feature set in a language like C Sharp, is that it automatically manages memory management. So rather than the programmer having to figure out, oh, I want to allocate this block of memory, and then I have to deallocate it, or I have to use different pointers or wrappers around that to free and deallocate that, Java is essentially handling that for the programmer behind the scenes, which helps simplify development. And pretty much most new languages that come out have some form of this, some form of memory management that's handled automatically at the language level. And Java runs on something that's called a Java virtual machine. So C Sharp is also, again, I mentioned C Sharp again because they're similar in the way that they're designed. So a language like C++, if you compile that, it compiles essentially very directly down to machine code, whereas Java goes to an intermediate language, which then gets compiled back down to machine code. And because there's this intermediary language, it provides a layer of abstraction that makes porting to different platforms simpler because the platforms simply just need to support the JVM in order for the Java programs to run. So talking a little bit more about the Java JVM, a virtual machine is essentially where you have these coded instructions, not that different from what you would actually see, at a CPU level. And those instructions are then essentially translated to bytecode, which is what the CPU then runs. So Java, like other languages that runs on a virtual machine, is typically going to be slower than its counterparts like C and C++. That said, Java has had quite a few under the hood improvements throughout the years. Obviously, when the language was first created, it didn't have a lot of this, so the performance characteristics were pretty stark in comparison with a language like C++ or C. But now you have just-in-time compiling, JIT, other different improvements, performance improvements, compiler improvements that make Java perfectly usable for production software. That said, if you're doing certain computationally intensive tasks, it may not be the best language to solve that particular problem, but in the realm of Android development, it's perfectly sufficient for what we're trying to do. So on Android, Android itself uses Java as its primary language. And what's interesting is that Android uses a modified version of Java that's optimized for mobile. And so the reason for this is actually that Android runs on quite a few different devices, and they can range pretty heavily from very low-end specs, very low-end processor and RAM, to the newer phones that have pretty good GPUs, pretty good CPU and memory. And because the Android OS or the SDK is essentially a layer or an entry point into the OS, they wanted to make sure that it ran on a variety of devices, that it wasn't sluggish on the lower end devices, but it only ran pretty well, or it essentially was performant on the high end devices. And there's a pretty common, you'll see it in most languages. Most languages will have a standard library for doing file IO or strings, networking, that sort of thing. So Android actually re-implements most of the standard Java library. So primarily, if you have come from the Java world, then a lot of the functions and capabilities that you would expect you're still going to find them when you're working with the Android version of Java. Now, also just talking about evolution. So Android as well as iOS has changed quite a bit. The landscape of both what apps look like, how they're built, the tools that are used to build them has obviously changed a lot since both respective app stores, the Play App Store as well as Apple's App Store are concerned. And, if you go back to 2010, an Android app, in terms of like if you looked at the code base versus an Android app built now, would look very, very different. Part of that is also just driven by market needs and the complexity of apps, and apps just becoming more data driven in terms of having a lot more interactions with databases and servers, whereas early apps weren't quite as sophisticated, or it was you could build things that were a bit simpler on the surface and didn't require quite as much nuance. So part of the reason, if we're unpacking why did this change occur, like why couldn't we keep building things the same way that we have in the past, is the fact that Android has really just expanded beyond just smartphones. So Android OS is on tablets, it's on smartwatches, it's on smartphones that again could go back to a 2010 model to a new Pixel 2020 phone, and the range of specs between those, and also the fact that they're running completely older or very cutting edge versions of the actual operating system. Uh, Creates a lot of challenges in being able to support all those particular device specs. But the main reason, though, has to really do with lessons learned from what are the main pain points of Android apps in production. And a lot of these common pain points have to do with managing what are known as life cycle events. So, life cycle events, we'll talk about them a bit later, but the gist of them is essentially whenever whether you're on iOS or Android, is pretty similar. If you press the home button and you exit out of an app, the app gets suspended. If you press the app icon and you go back into the app resumes. If you take a call, like a phone call, in the middle of an app, then the app will get suspended. And additionally, if an app, let's say, is suspended or it's in the background, if you opened like a memory intensive app, let's say like a gaming app, a Candy Crush, or maybe something a bit more heavy duty than that, the OS on both iOS and Android has essentially the freedom to terminate whatever it wants to terminate in the background in order to free memory. And if you have an app that, due to programmer errors, essentially leaking memory, which means that memory, the longer the program runs, the more memory that gets lost, the OS at a certain point may terminate that. And so what does this result in? Well, this essentially just results in users perceiving a very unstable app that's constantly crashing. And the reasons are crashing because of edge cases of lifecycle events not being essentially subscribed and unsubscribed in a clean manner, and memory leaking as a result of not correctly disposing of resources. So this ties in with a core concept that you'll hear a lot in different circles in programming, called data-driven UI, and we'll continue to talk about this. What does this mean? So data-driven UI is essentially about separation of concerns. So you want to take your data. So if you have a Facebook app, so the data could be the user data or the feed data, and you want to completely separate that from how it's actually being rendered, so that those two components have very little knowledge essentially of the other one at all. And observing the changing of state, inside of a view, which you can think of as a screen in an app, is essentially what's going to drive our UI. So we'll continue talking about this, and also talking about how this is something that the Android team itself at Google became aware of a lot of these challenges, and also just they came up with some different approaches for app developers, just given the fact that apps have just gotten a lot more sophisticated over time. So one of the approaches that they recommend, and part of this is actually supported with some libraries that they put out later, is these 4 components that you will see in an app. So number 1 is you have something called an activity. Number 2, you have something called a view model. 3 is a repository, and 4 is a model or a remote data source. So just at a high level, you can think of these basically as, let's say you have a camera app, and your camera app screen where you're taking photos is essentially your activity. Your activity is the nucleus of being able to do one discrete action. What is the view model? So the view model is essentially, it's going to hold all the data that would be needed to render a particular screen. So in this case, it would hold all the state for this camera taking screen that you're on. What is the repository? So the repository could be, let's say you're in this camera app and you have global user-wide settings of users that have signed in, let's say, with like a Facebook account or they've linked an Instagram account, and that's just something that you globally want accessible in the app. That would be stored in a repository. And then the model or the remote data source is something that the repository could then talk to, where a model would be, let's say, like a local database, like a local SQL or SQLite database. And a remote data source would be, a server or a server endpoint on the internet. So the overall flow would go from activities, you're kind of your high level manager. View model is holding all the data. Repository, all the data for one view. Repository is holding all the data for the app. And then the model or the remote data source is actually where you're grabbing that data from, whether it's locally or from an external internet accessible source. So I know that was a lot to take in. Good thing is that the Android team is aware of the complexity of all that, and so they've created a set of best practices and architecture components to help make this process a bit easier, so that you're just not having to go and even figure out where to start with building an app and doing it in the way that they recommend. There's different libraries that exist that have tried to address this, and typically what you'll see with pretty much any app framework is over time you'll have third-party libraries that come out, and then the app framework developer will usually migrate or figure out, a large portion of our developer user base is using something like RxJava, so we should probably build something similar in-house because this is just a wide product need. What are some of these architecture components? Well, you'll see live data, view models, which view models we described a few slides back. Mediator live data. These are the bread and butter of what you'll be using to essentially create this separation of concerns for a data-driven UI. We're not going to talk explicitly in detail about them, but just be aware that those are terms and particular classes that you'll see come up quite a bit. Now, you might be saying, well, we've been talking about Java, but what about Kotlin? Shouldn't we be writing our new apps in Kotlin? And so the answer is maybe. So Kotlin's a new programming language that's pretty similar to the paradigm that Apple introduced with Swift, having a new programming language that kind of addresses the pitfalls and has a lot of syntactic sugar in terms of just making programming a bit more enjoyable and having shortcuts for doing various common commands. So Kotlin is a great language, but that said, it's still totally possible to be writing apps for Android on Java. And in terms of what does Google recommend? Well, when it comes to certain things, Google does recommend you probably should go with Kotlin, because otherwise you're going to have to use some third-party libraries to achieve the same functionality, and it just tends to be a bit cleaner to use Kotlin. And like Swift, where you can intermix Objective-C and Swift code, because a lot of apps were written primarily in Objective-C, and then Apple wanted to give app developers the ability of mixing and matching Swift for parts of the code base. You can also intermix Java and Kotlin, which is pretty cool because they can interface with each other, call each other, and then you can get access to a lot of functionality inside of Kotlin, even if you decide to write most of your business logic in Java. So for the purposes of what we'll be doing over the course of these next lectures, we'll stick with Java. That said, given how heavily Google does emphasize certain aspects of the code being written in Kotlin, and it does simplify definitely certain problems with concurrency, we will write small sections in Kotlin, but primarily the business logic will be written in Java. And this is also just a useful approach to get used to, because in the real world, you might join a team or hop onto a project where they've already written the bulk of the code in one language, and figuring out how to write certain aspects that make a bit more sense in a new language without rewriting the whole code base is just a good skill to have. And talking a little bit more about why we would use Kotlin for something that you might go, well, is it that big of a deal? And honestly, it is actually a pretty big deal. So Coroutines are addressing an issue that you'll see it's very common in the mobile space where you want to perform an asynchronous task. So synchronous task would be I want something to happen essentially immediately, whereas an asynchronous task would be if you are doing an action that can take a variable amount of time. So that could be I am making a call to the back end and sending some data to the server. Well, you don't know A, if that call will succeed, and B, if it does, how long it will take based on, the user's Wi-Fi connection or 4G, 5G connection. It could be loading a file locally from a database where, again, you don't know how long that's going to take to exactly read or write from that. And Kotlin in the language itself has very strong support for coroutines, which essentially simplify a lot of the nasty bits of writing concurrent software with, some of the primitives that you would typically see that could be confusing for different programmers. And Google, again, is just very emphatic about highly recommending using it. So we're going to stick with that paradigm for these lectures. Now, I always love just starting with the simple stuff. Where's the entry point? That's usually my first question when I start digging into figuring out a new framework. And so in Android, it's onCreate. So what is onCreate? Essentially, onCreate is a function that is called, when the app starts up. But it's not alone. So it's part of a family of what are known as lifecycle methods. So as I mentioned earlier, app can easily be exited, like the user quits it, or it could be terminated by the OS. It could be suspended or paused. It could be sent to the background. It could be listening in a background state. There's a lot of different states that an app can be in. And so onCreate is part of that same family of events that you can listen for. Now, I'd mentioned activity before when we had talked about the overall architecture components of how you structure an app. And the best way of thinking about an activity is it's a single focus thing that the user can do. So for example, again, it could be you have your photo app, it's taking pictures. It could be I want to open up an MP3 player, play some music that I have locally on my device. So an activity essentially is the manager for lifecycle events. It doesn't actually render UI, but you can think of it as that high-level manager for the OS events, and it's going to receive all those events that happen periodically through an app running either in the foreground or different system events that cause it to exit or go into suspension. Another common question that I always have is how do I get something actually running on a device? And it's definitely pretty cool when you see even just a little sample app running on your phone. So it actually ends up being pretty simple. There's more documentation in the Android portal, but the gist of it boils down to you plug in your phone. There's a couple of settings that you tweak to enable your phone for being a developer device. You hit run, and then Android Studio pretty much does the heavy lifting and gets the app installed on your device. Compared with iOS, where getting an app installed on your device is usually a little bit more of a pain in terms of how locked down the platform is and just different hoops you have to jump through. For Android, it's pretty easy for Android Studio to use a build system called Gradle, which figures out what dependencies your project has, what should actually go in the final executable, which is called an APK, and then it just works, and you'll see it running on your device. So one common question you might also have is, okay, well, I'm used to having apps with different screens. So how do I actually navigate between them? So intents are something that the Android OS supports where you can navigate or essentially communicate between one activity to another. So each activity is only responsible for one task. So an example of this would be actually at the OS level. If you're on an Android device and you go, oh, I just downloaded this MP3 file and I want to play it, the Android OS will pop up something saying, hey, which app do you want to use? And based on what the user selects, it's actually sending an intent to that app saying, hey, uh, we have the intent of opening this app, your MP3 player app, and we want to navigate to this particular activity within the app to address what the user is trying to do. So, given that Android is a very flexible platform, just philosophically in terms of how they approach it, of users being able to download apps, interchange apps that are used for core system functions or messaging. This actually makes a lot of sense that the user can mix and match which apps they install for core system tasks. So then you have activities, but then where do you actually store the data for what's on screen? So view models are responsible for actually holding the state or the data that one particular screen needs to operate. It's something that Google highly recommends. It provides, again, that clean separation of data from the actual UI rendering code. And view models can then be essentially observed using a subscription publisher subscription pattern to give the UI an opportunity to observe for those changes and then react by updating the UI. But you still may be asking, okay, we've gone through a lot of these high level abstractions. I still want to get something on the screen. That is a very good question. But I still have to caution you, and this is again coming straight from the mouth of Google, that activities are, again, a top level lifecycle manager. You should never be writing UI code inside of an activity. But where then do we write their UI code? Because view models are just data and activities are just the high level events and kind of the glue for our application. So you have something called fragments, and fragments are where we're going to write our UI code. Now, what's cool about fragments is they're essentially widgets. This is a concept that's become really popular in different mobile frameworks. It's common in Flutter, which is also another Google product for building cross-platform apps. And fragments are essentially like widgets. So you can think of them as, like, you could have a drop-down menu fragment, you could have a tab bar fragment, you could have a pop-up fragment, and then you could interchangeably nest and, combine fragments with each other to create, essentially new UI. And then this gives you a much more modular and flexible approach because you're essentially using a pattern of composition to arrange your UI so that it's really easy to swap out one component, or if you didn't like, for example, having a button that was styled a certain way, you could easily swap in a new one and your application would work just fine. So, so we did touch on a little bit earlier about talking about intents and how they can be used at kind of an OS level to actually open an app. They can also be used to navigate from one activity to another. So within, let's say, a camera focused app, you could have an intent within the app to say, hey, I want to transition to something that can view all the pictures that I've taken. And then you can also pass different data from that along the chain to say, hey, I want to pass certain information to the gallery, so it can initialize a certain way. Again, another common question that I usually have is, well, that's great thinking at a micro level of, okay, I've got a screen, but I'm still running an entire app, and apps typically have some top level state. So that could be, if you're in a Facebook type app, that could be you have your account settings or your user data of like your name and where you went to school, who are your friends, your connections. And that might be something you might want to globally persist because it could be used in different portions of the app. So in the Android world, it's held in essentially something called a repository for state that you just typically, it wouldn't make sense to have it be owned by one particular view model. Cache data is also another great place for that as well. If there's data that you cache when the app loads up or in startup, and then you'd want that to be globally accessible, putting that in a repository could be a really good option. Okay, so essentially what I just wanted to do with this talk was give you a good overview of the high-level concepts of what it looks like building an app on Android in a production level way so that you're following the right patterns that Google recommends, that the Android development team recommends. And so next week, we're actually going to get hands-on with an app to gather research data. So we're going to start getting into drawing things on the screen, gathering data, saving data, loading data. So it's going to be pretty exciting, but just wanted to start off simple, give you a nice quick overview, and we'll just take it from there next week. Looking forward to it.